Hey everyone. So in this video, I'd like to talk about function notation. So we defined a function in the last video, and we said that it was a relation in which each input leads to exactly one output. And we can also think of this as saying that the input of a function completely determines the output. That's what's sort of special about a function. And so we'll constantly be working with functions, and we'll want to be able to do a few things. One thing is, let's say we have a few different functions we're working with. We want to be able to easily refer to one of those functions, point out a particular function amongst a crowd. Another thing we want to be able to do is to very clearly and concisely express inputting into the function, right? Inputs in the functions are so important because they determine the output. They completely determine the output. And so we want to be able to very quickly and simply be able to talk about inputting into a function. And so this is the idea behind function notation. This is notation that we've built up to be able to do these two ideas. Okay, so let's use this equation here to really introduce this idea of function notation. So here, this equation is y is equal to x squared plus 5x minus 6. One thing I want you to notice is that here, the values of x actually completely determine the value for y. Right? Squaring a number is only going to give me one result no matter what number I square. 5 times the number is going to give me one result, and adding or subtracting these quantities together, it's only going to give me one result. There's not going to be any ambiguity. I'm not going to get two different results for one value of x. And so here we can really think of this equation here as a function. That y is a function of x. I can think of y as my output quantity and x as my input quantity. Okay, so this is a function. And one thing I want to mention is that just like we can give variables names to refer to them, we can give functions names to refer to them. And so one thing I might do is I might call this function, maybe I'll call it p. This choice is kind of arbitrary here, but I'm just showing that I can name this function p. And oftentimes we'll include, beside the name of our function, we'll include a parentheses with the input quantity, the input variable inside. So here I'm going to say p, this is usually read as p of x. And so the thing I want to point out is that p is here to represent the name of our function. And then this parentheses x is here to represent the input of our function. Very importantly, not multiplication. And so if I'm going to call my function above, y is equal to x squared plus 5x minus 6, if I'm going to call it p, one way I can do so, or sort of make this very clear, I can say p of x is x squared plus 5x minus 6, right? So here, this again completely determines the outputs. And so p is going to be this function, it's going to be the outputs of our function given by the input x squared plus 5x minus 6. So these are really describing the same thing. Okay, so here, one way we can describe inputting into this function is using this sort of, this parentheses x part. Right, so for example, if I wanted to describe inputting the number -2 into our function, replacing that input variable x with -2, well, I would write that as p of -2. Right, so this reads as, this is inputting -2 for the input variable of our function. And then determine the output. right? So really, if I wanted to determine p of 2, and here I've, p really represents our function above, p of negative 2 would look like, well, I'm going to plug in negative 2 for x. Right, everywhere I see x in my function, my input variable, I think it was minus 6, right? And so we get out 4 plus, so actually this should be minus 4 minus 10 minus 6. So 4 minus 10 is negative 6. Right, if I have $4 and I owe $10, well, at the end of the day, I could pay off some of that debt, but I still owe $6, right? So here, this part is negative 6, and then minus 6 again gives me minus 12. If I owe $6, I owe another $6, I'll owe $12. Right, so this is telling me that my output corresponding to an input of negative 2 is negative 12. So usually we'll say that P of negative 2 is equal to negative 12. Right, so here again, this negative 2, that's an input. This negative 12, it's our corresponding y value, it's our output. And you can sort of think of P of negative 2 as the output corresponding to an input of negative 2. And so to to say this a little bit more generally, frequently we'll use f and g and h to name our functions, to label our functions, just because of f for function. So these are commonly used to label functions. And in general, if you see a statement like f of an input, well, that means to determine the output corresponding to that input. So f of an input tells us that represents the output corresponding to that input. Okay, so we can also, actually no, I'm a little bit ahead of myself, let me go back. So we've input negative 2 into our function above, and we saw how that looks. We can even more concisely communicate complicated expressions, right? So I can do something like, I could say, well, let's compute p of negative 2 plus p of 3 minus 11. So what does this mean? Right, so this means input negative 2 into the p function. Right, so this concisely says we'll square negative 2 plus 5 times negative 2 minus 11. Right, because that's our function above is x squared plus 5x, why did I say minus 11? It should be minus 6. Minus 6, right? So our function above is p of x is equal to x squared plus 5x minus 6, and this is just saying replace x with minus 2 and compute the result. And similarly, this is saying compute the result where we let x be replaced with 3 in our function, right? So this really means take 3 squared, add 5 times 3, and subtract away 6. Right, so this p of 3 represents the result from plugging in 3 into our function. Right, so what we really get here, at least in p of 3 is equal to, that's 9 plus 15 minus 6. In other words, that's, well, 9 plus 15, that's 24, minus 6 is 18. And we know that we already computed p of negative 2 earlier. Right, we said that it was negative 12. Right, so really this expression, it's the same as saying, it's the same as saying this whole quantity added with this whole quantity, take away 11, and we've just determined that that's negative 12 plus 18 minus 11. So negative 12 plus 18, that's positive 6. And then minus 11 gives us a total of negative 5 out at the end of the day. So that's this expression. But we were able to very concisely say so much in this small statement. One thing I want to warn you about is that, right, so again, that parentheses negative 2, again, that's just a way of describing inputting into the function. It has nothing to do with multiplication as is. But one thing I also want to mention is that p of negative 2 and p of 3, these things don't combine in any nice way. This really just means compute the output when we input negative 2 for p. And this means compute the output when we input positive 3 for p, and then add them together. Right? One thing I want to say is that this is not the same as p of negative 2 plus 3, so it's really not the same as p of positive 1. Okay, so this whole process of plugging in an input to a function is called evaluating. Right, so here what we were doing was we were evaluating p at negative 2, our p function. We were evaluating p at positive 3, and then we were adding the results and then subtracting 11. So we can also evaluate functions with more complicated expressions. For example, let's say we've got the function g of k. Right, let's say that this is equal to k squared minus k plus 1. Right, so this is saying that g of k, it represents our function, our outputs. It's saying that our input variable is the variable k. And if I wanted to describe inputting into this function, I would replace k here in parentheses with our input. And that would mean that we would replace any k we see in this expression on our right with that input. Right, so here, like I was saying, we can evaluate these functions with more complicated expressions. Let's go ahead and maybe do that one example of that. Let's evaluate g at a plus h and subtract away g of a. Right, so this just means take our g function, and wherever we see our input variable, plug in a plus h. That's what this part means. And the second part means for our g function, again, wherever we see our input variable, plug in a, and then subtract these two results. So let's go ahead and do that. And so maybe I'll use blue to represent the inputs for these functions, but this first part, g of a plus h, right, that just means take our input variable, and wherever we see it in our expression, replace it with a plus h. So here I have a plus h squared from this first part, right, squaring our input, squaring a plus h, and then we're going to subtract away our input, so minus a plus h, and then we're going to subtract away, we're going to add away, or add 1. Oh, actually, sorry, I reversed the colors. This should be in green. Did this slightly differently in my notes. So here, a plus h squared minus a plus h plus 1. So that's this green part here. And then our blue, or our purple part, right, just amounts to plugging in a into our function here. So we're going to square a. We're going to subtract away that input of a. And then we're going to add 1. Right, so that's the purple part in our expression. And then we're going to subtract these results from one another. Okay, so here, maybe before we really do much more, let's go ahead and compute this a plus h squared. I think that's going to be helpful for us in this long-winded problem. So a plus h squared. Right, what does that mean? What does it mean to square something? It means to take the base and multiply it to itself, right? So a plus h times a plus h. And so when we multiply two polynomials, well, what we have to do is multiply every term in the first polynomial with every term in the second polynomial. So I'm going to take a times a to get a squared, a times h times a, and then h times h, so h squared. So this comes out to be a squared plus ah and ha. I can really think of that as 2a times h, and then plus h squared. One thing I definitely want to emphasize is that this is not the same. Right, this is not equal to a squared plus h squared. Right, we didn't just square each term. Really, we had to square the entire group. Okay, so that's that part underlined in pink. Let's go ahead and sort of put that into our expression. Right, so here we've got a squared plus 2ah plus h squared. And then we have minus a. And then, right, so this is going to tell us to subtract a plus h. So subtract away a, subtract away h. You can kind of think of it as distributing through that subtraction. And then we have plus 1. And then here for this latter, this purple part, right, we're going to subtract it away. So again, we can kind of think of it, this is subtracting away that purple group. So I'm going to subtract away, or we could essentially distribute that subtraction sign. I'm going to subtract away that a squared. I'm going to subtract away minus a. So that gives me plus a. And then I'm going to subtract away that positive 1. So that gives me minus 1. And then these parentheses don't really do anything, these brackets, so maybe I'll just erase them. And so notice that we've got this a squared, we've got minus a squared, we've got this minus a and this plus a, and this plus 1 and this minus 1, that all cancel out. And really what we're left with at the end of the day is 2ah plus h squared minus h. And so this is the result, this is what we get from evaluating our sort of crazy expression above. Okay. One more thing I want to say, one more piece of terminology is usually, you know, when we do the reverse, when we know an output of a function and want to determine an input, we call this solving. All right, so for example, let's say I want to solve g of k is equal to 3. Right, this is saying that, you know, I know my output is equal to 3. Find the corresponding input, the value of k, that gives me the output of 3. Right, so this is saying the output is 3. Right, g of k represents the outputs of our function. The output is 3. Find the input. Right, so I'm going to set 3 to our output. Right, 3 is equal to, what is this? 3 is equal to, and again, we're talking about our g function, which was k squared minus k plus 1. K squared minus k plus 1. And so to figure this out, we actually end up needing to solve this equation. And that's why we use this term solving to sort of represent this idea of taking an output and finding an input, because it usually boils down to solving an equation. And so one way we can solve this equation is it's a quadratic equation. There are a few different ways. We can try and solve by factoring. We can use the quadratic formula. We can solve by completing the square. These are all different options, but let's go ahead and try to solve by factoring. Usually that ends up being the simplest if it works out. So I'm going to try and solve by factoring, and to do that we need to make one side equal to 0, and then factor the other side. So let's subtract 3 from both sides. And then now we want to try and factor this other side, right? So this non-zero side. So here we've got 0 is equal to, how does this factor? This can factor as k minus 2 times k plus 1. And so now, when is this true? When do we get solutions to this equation? We're asking for when two quantities multiply to 0. That only happens when one of the quantities themselves is 0, right? We can only multiply things together and get 0 if one of them is 0. And so either k minus 2 is 0 or k plus 1 is 0. Right? These are going to lead to solutions to our equation. So k is equal to 2 or k is equal to negative 1 are going to be solutions, and these are values of k that lead to an output of 3. And I would encourage you to check this out, plug in these values and confirm this yourself. Okay, so everything we've described so far has been, or at least for function notation, has been in terms of equations. And so I want to take a moment to mention that these ideas also apply to graphs and tables. So I've got a graph here, and I've labeled it Q of M. This is just saying my outputs Q for this function are determined by the inputs M. Okay, so one thing I want to point out is that maybe you haven't seen this before. We've got this open circle for this graph here at the very end. This is saying that that point is not included. Right, we said that a graph represents a bunch of points. It's describing a bunch of ordered pairs, and the ones that are plotted out and drawn out are included in the set of all those ordered pairs. This point, this open circle here, is just to really indicate very clearly that it's not included in the set of ordered pairs. This point, negative 4, 5, it's not associated to this graph. And then this closed filled in circle is to say this one is. This is a point on our graph. So here this is included. Okay, so here when we say something like solve Q of M is equal to 5, again this just means find, so here this is saying that our outputs are 5, find the corresponding inputs that lead to such an output of 5. Right, so an output of 5 is like saying our vertical component to these points, our vertical coordinate should be 5. What horizontal coordinate should we have to get that output of 5? And so you can see on our graph here that our outputs of 5 occur, well, there's one point here with an output of 5, there's one point here with an output of 5, and this point, it has an output of 5, but because it's not included on our graph, we're not going to pay attention to it. So really, we have solutions when m is equal to 2, or when m is equal to 4. These are both inputs to our functions that leads to an output of 5. And then another thing I should say is that when we say solve, just like when it comes to solving equations, this means find all the values that do the job. Find, when we solve an equation, we're saying find all the values of the variable that make the equation true. Here we're looking for all the values of our input that give us this output of 5. Okay, this next part says evaluate or find Q of negative 3. That means to evaluate our function Q, where our input is negative 3. Find the output. So here we have an input of negative 3 at this point, negative 3 comma positive 2, and so Q of negative 3, this is positive 2. We have this output corresponding to our input of negative 3. Okay, so for tables, we have this table here. I've created this example here, and notice that this is a function, right? We don't see any repeated inputs, so that's telling us that there's not an input that leads to two different outputs or more. So every input has exactly one output. This is a function. And so let me say that the outputs of this table, let me label them by this function f of x. So now, really, when I refer to my function f, I'm talking about the outputs of this table here. Let y be represented by f of x. So sometimes you also see this. You see your function notation in the table. You might see this as x on the left column and f of x on the right column. These are both the two different ways of sort of describing the same thing. So here we want to evaluate f of 2. This means find the output when the input is 2. Right, and so here we have an input of 2 in this first ordered pair. And so our output is this value 3. Right, so here f of 2 is equal to 3. And then our next statement says, okay, solve f of x is equal to 3. We're saying our output is equal to 3. Find the corresponding inputs. Right, so here we've got an output of 3 here on this table, and we also have an output of 3 here on this table. We want to find the corresponding inputs. Right, so here we have an x value of 6 leads to an output of 3. F of 6 is equal to 3, and also f of 2 is equal to 3, as we saw above. Right, so x is equal to 2 leads to an output of 3. F of 2 is equal to 3. Okay, so that's tables and graphs. We'll also often want to use functions to represent real life scenarios, right? So here, let's say I've got a function h of t, and it gives me the height in feet of a ball t seconds after that ball is thrown into the air. And so here's the function or an equation that sort of goes with it. H of t is equal to negative 16t squared plus 40t plus 5. And so one thing I want to ask is, what is the meaning of h of 2? Right, so in our description above, right, h of t, these are the outputs of our function. And we're saying these outputs give us the height of the ball. Right, so here what I want to say is that the outputs, they correspond to the height of the ball. And our input variable is t, and we're saying that t represents the seconds after the ball is thrown. Right, so here this is saying that our input variable is kind of representing time. It's the time in seconds. And so this is kind of an important idea to have in mind is not just how to input into a function, how to recognize outputs, but also being able to recognize what these inputs and outputs mean for the particular problem. All right, so what's the meaning of h of 2? Well, this is saying we're inputting 2 into our function. We're saying that t is 2, or in other words, 2 seconds after the ball is thrown. And that's what an input of 2 means, but h of 2, that tells us that means the height. Right? So this is the height of the ball after 2 seconds. So when we compute in our function, when we plug in 2 into our function and compute the result, what we're really finding is the height of the ball after 2 seconds. And so maybe we can go through this just once real quickly. So h of 2, right, so our function says take negative 16, multiply it with our input squared, and then add 40 times our input, and then add on 5. Right, so here order of operations tells us to square this 2 first, right? Not this negative 16, that's not included in the square, right? Because they're separated by multiplication. Here we have negative 16 times 4 plus Okay, now we have 40 times 2, that's 80. And then we have plus 5. Okay, so 16, negative 16 times 4, that's negative 64. We have plus 80 plus 5. This is, what is this? Negative 64 plus 80 is positive 16. Plus 5 gives us 21 out at the end of the day. So really the height of the ball, it's 21 feet. The ball is 21 feet in the air 2 seconds after the ball is thrown. And now in this last example, what do the results of solving h of t is equal to 14 mean? Right, so h of t is equal to 14. This is telling us that our outputs, right, after we plug in some value for t, our output is 14. Right, and we said that earlier. H of t represents the height of the ball. The outputs represent the height of the ball. And so when you solve for this output, you're finding the inputs that lead to these outputs, leads to this output. Right? So this essentially means find the time when the ball is 14 feet high. Right, so this amounts to solving the equation, right, letting our output be, what is this? This is 14. Letting our output be 14 and trying to find our corresponding input that would lead to this output. Right? Trying to figure out this result means trying to solve this equation here.